I get a different display than the students get. And so if I want to make sure that the thing that you see looks like I wanted it to look like, I have to log in as a student. So I have a test student that I can pretend to be a student and log in. But like I said, I'm not real good about doing my homework, so I haven't done any of that stuff. And so these people, I'm guessing a lot of them are probably in that category where they have something that's submitted but not graded. So I'm not really that concerned yet. It's early in the term. We've still got a lot of points left. My intention in that gradebook on Blackboard is that every point that you see is a point on your final grade. So then when we're all done, the total points available for all of the assignments adds up to 100. Actually, it'll add up to 102 if I did the math right. So there's already 2 bonus points in the equation. So anyway, take a look at yourself in the gradebook. If you're concerned that your grade isn't what you think it should be, let's talk about it before the term's over, not after the term's over. All right, so grade distribution, grades, we took care of that. What's today really about? Right, I think today we're supposed to talk about energy and power. Oh, have you guys done with the cards? So put them grade side down. Grade side down. Pass them to this guy in the front that doesn't have his name tag. So Xavier. Pass them to Xavier, grade side down.
What about my hand?
Yeah, pass them to Zeb, and then he can hand them off to Xavier. See that? That's the power of delegation right there. Energy and power. What are the units for energy?
Joules.
Joules. Excellent. I'm so glad that we're using a metric system, right? Joules are metric, right? Energy, the energy for units. The units for energy is joules. What's a joule? Somebody said it. I heard it. What's a joule? Newton meters. That's capital N, right? N's in capital N. And a little m. We got our units going. So energy is Newton meters. What's a Newton? Kilogram. What was it again? So Newton is kilogram meters per second squared. So joule is kilogram meter per second squared times a meter. So this is energy, right? What's work? Work is force times distance. Right? Work is force times distance. So does energy equal work? So Andre says no, not necessarily. So you're saying that energy equals work. You guys want to arm wrestle about it? We can settle this like Ben, right? It's a try like combat, right? Right? So Zeb says no, Andre says yes, but he sort of hesitated, right? So why do you say that they're different? Go ahead, Chops.
It's numerically equal, but conceptually it.
If I'm an engineer, if the units are the same, it's the same, right? Okay, but why is it different?
Because it's what you need to put into something for it to be able to do work. Like
So work is sort of a change in energy. Would you buy that? Work is the amount of energy that it took to do something. All right, so energy and work have the same units. One of the things we like to say is that energy is the ability to do. Energy is the ability to do work. Does that kind of make sense? All right, so energy, force times distance. You know, I wanted to work, but I didn't have the energy. Damn it, no power. What's power? Anyway. Power is like work, the derivative of work with respect to time, right? Power work over time. So power is work over time. Energy is Newton meters, force times distance, force times distance. Okay. So in everyday speak, so my haiku was about work, energy, and power, right? In everyday speak, we talk about energy, we talk about work. What do we mean when we say I didn't have enough energy? So I used up my energy by doing work, right? So I've got to change. All right, so I get that. So it's sort of equivalent, the life speak and the engineering speak. Now, as a manufacturing engineer, why do I care about energy? We are still going to talk about the things that manufacturing engineers care about. As a manufacturing engineer, why do we care about energy? Energy costs money, Xavier said. Somebody said we pay our electric bill. Was that, wait, Jia Cheng? Jia Cheng. Okay. So we pay our electric bills. Energy costs money. Why else do I care about energy as a manufacturing engineer? So it costs me money, right? You fixing something? Okay. It's fixing something. It's on something. Why do we care about energy as a manufacturing engineer? It costs money. We got that. So it adds to our cost. So we're trying to increase our profit or our profit rate. It adds to our cost. We want to be efficient. Wasting time, like saying haikus in class. No. Yes. Right. So one of the things we're doing in our transformation process, so that energy costs us money, but we also have to put energy into our materials in order to transform them. Right. I don't think there's any manufacturing process that doesn't involve doing work on something. I think every manufacturing process, whatever it is, assembly, it all involves doing some energy or putting some energy into it, right? Okay, so what happens when we put energy into something? Go ahead. Well, the price goes up, yeah, because we pay for the energy. But I'm just thinking about, so I could put energy into this hand, right? By hitting it with the other hand. So I can put energy in fact, I still feel that energy is tingling. Right? Ooh, I can market that. I got an energy enhancer. Just hit yourself and feel it. So what do I do when I put energy into something like that?
I was thinking about, first off, either add heat or work or control.
thermodynamics happens, right? So if we put energy into something, one of the things that almost always happens is it gets warmer, right? So by adding energy to something, we almost always make it warmer. And so we're putting the energy into our material in order to change it. Energy is our ability to do work. Work equals force times distance. Power and energy are related. Power, again, what? Energy over time. So if we're looking at power, how do we measure power? How do we measure power? Yeah, let's start with units. Watts a watt, right? That's capital W. Power's a watt, right? What's a watt? It was on the last page, right? Joules per second. All right, so watt equals joules per second. How else do we measure power? Who's into cars? You can still answer if you're not into cars. How do we measure power?
Force and velocity.
Horsepower. Force times velocity. Power is force times velocity, right? So now we talk about the units of power. If you're in a machining operation, how could you measure power? What else is power besides force times velocity? Any W's in the room? Really? No W's in the room? Nobody wants to admit it, huh? Anybody had E for dummies? All right. So how else do we measure power? It was dummies. Current times voltage, right? Amps times volts, right? So we can measure power, and so how do we measure things like amps and volts? With an amp meter and a voltmeter. Those electrical engineers are not very what's the word? Creative in their naming of their tools. Amp meter, voltmeter. You could use a multimeter that measures both of them, right? So we can measure power pretty easily by measuring the current and the voltage going into our machine tool. And then we can know how much power it took to cut something. Why might we want to know how much power it took to cut something? Yes?
To make it more efficient.
So we might want to make it more efficient, right? Because we're paying for that power, that energy as it comes in the door, right? So we're paying for it. We might want to make it more efficient. Why else might we want to know how much power it took to cut something? Go ahead.
To get an idea of how much it would cost.
We could get some idea how much it would cost. Anybody else? Somebody said it earlier. Hey, we would like to know, anybody know what it sounds like when your machine tool does not have enough power to make the cut that you programmed it for? It sounds, let's do a mini mill. Okay. That's sort of a mini mill spindle, about 6,000 RPM, right? Oh! That's kind of what it sounds like when your mini mill does not have enough power to make the cut that you're making. So the one way we overcome that is to get a really heavy tool holder. Take it through, get a really heavy tool holder, and we get it spinning at 6,000 RPM out here in space before it touches the workpiece. That's what it sounds like. And depending on the setting on the machine, it will actually alarm out if the decrease, or if the increase in power is above a certain level. So maybe those mini mills, they've got a needle on the front, right? It shows you that what that needle is showing you is the power going to the spindle motor particularly. So it's not showing you the power coming to the machine as a whole, but just to the motor that drives the spindle. We're straight up on the meter. Anybody notice it? Straight up on the meter is 150%. I'm pretty sure the scale has to do with marketing. And you can run our machines at 150% power all day long and they won't blow up. Anybody ever notice that you tend to drive with the needle straight up when it's thermometer, regardless of the position that is straight up? I figured that out when I was riding with a friend who, let's just say straight up in his car was 105 miles an hour. But you know, straight up my car is like 70 miles an hour. I go 70, right? But when they changed the speed limit, they actually moved the point on the dial. It was straight up. They know this. It's psychological. But so that percent power that it's outputting or telling you there on the screen, that is the percentage of the total power available at the spindle at that spindle speed, which is why they don't have units on the side, because depending on the spindle speed, there's a different amount of power available. There's a power curve associated with those motors. So we don't want to run out of power. Thank you. What else don't we want to do? Power equals force times velocity. If we're cutting the material, where's that force being applied? It's being applied to the workpiece at the chip. And if it's steady state, we get that damn equal and opposite force thing going on, right? Which means it's being applied to the tool also equally, assuming we're not accelerating our part out of the device. Somebody had that happen, right? That person's not in the class? Not here anymore? Somebody had that happen. It was like a $400 window. And I suppose it wasn't your fault that the PLA didn't tell you to tighten the device. You were there. Hey, was that loud? Yeah. Did it make you jump? Did anybody say, holy shit? Yeah. Yeah. That was our bad. They should have told you to tighten the device.
I was actually going to ask them because I know it's
Too late, huh?
Yeah.
Yeah. So would the emergency stop have helped?
Yeah. I figured it was
Before the tool contacted the workpiece, right? So what is that? For anybody that doesn't know, there was an instance when one of the laboratories was starting making those Y blocks, and we had one of those heavy tools. Not only that, we had a spindle with 30 horsepower, so that tool wasn't going to have a problem anyway. But we had one of those heavy tools, and they hadn't actually. Remember there was a torque setting, we had to torque the device closed. They skipped that step. The PLA didn't tell him to, and hey, he's never run a machine before. And he was thinking about it too, but just not fast enough. So what did you observe when what's your conclusions about the energy in the charge? There was plenty of energy, right? So that's like car windshield glass, and it didn't go through it, but it certainly broke it. $450 to replace, not to fall. The PLA did right, and I broke this email. You guys heard about I broke this, right? Yeah, okay. And so we actually collect a thing, and that's how we developed that operator checklist that we made to get use. And I figure that operator checklist cost us about $90,000 in repair bills to develop. That is a valuable checklist. On the other hand, since we deployed the checklist, we have not had any expensive crashes. This one was kind of expensive. We've not had any expensive crashes that would have happened if somebody hadn't skipped 20 steps. Every single crash that we've had since we deployed the checklist happened because somebody skipped 20 steps. All right, so energy equals power, or power equals force times velocity. Force is important because, one, well, it can project our part if it's not clamped. Two, it can break our tool. Anybody heard of tool break yet? Those 3/8 mils you guys use? It's about what they sound like when you're right next to the machine. They sort of explode when we screw up. And so we want to make sure we don't run out of power with the machine. We'd also like to have some idea, can the tool withstand the cutting force? And so cutting forces could range from tens of pounds to thousands of pounds in these operations. So that's why we look at, and power is really easy for us to measure, right? We can measure power pretty easily. Let's talk about estimating power. What are the factors you think that go into figuring out how much power it's going to take to make a cut? Because it's kind of on the tool manufacturer to make sure the tools are strong enough, right? We're going to put that on them. They tell us our feeds and speeds. The tool breaks, it's their fault, right? Spindle speed, mass. Okay, so we've got spindle speed and the mass of the spindle. And so there's going to, and I guess we need to think about friction in the bearings also, right? So if what we can measure easily is power that goes to the motor, right? So I got a motor. I'm going to label my motor M. I've got power going in, right? Coming out, what do I have? I have spinning, right? All of our machines are spinning machines. So I have spinning. And how do we do cutting? We take the spinning, and then, but the spinning alone doesn't cut anything. We take the spinning tool. With the spinning tool alone, do I look like a spinning tool? Okay. The spinning tool does not. The spinning tool doesn't cut anything by itself either. What do we have to have in order for cutting to happen? Right. We have to have the spinning tool engaging the workpiece material, right? So when we're cutting, we have to be making a chip. That spinning tool has to be engaging the workpiece material. So I've got. So how does the cutting edge of the tool engage the workpiece material? I mean, we know it's spinning, but when we zoom in on that tool engaging the workpiece material, what's it look like? When we so what's it look like? I got my cutting edge of my tool, right? So how does it move through the workpiece material? It has velocity, right? So let's say the cutting edge of my tool is moving that direction. At some velocity v. And here's my workpiece. Here's my new surface on my workpiece because we just cut. Right? I've got some chip that's flowing in that direction. So that's how the cutting happens. All the cutting happens is moving that sharp edge of the tool. Now, in our milling machine, that sharp edge is making sort of a helical motion through the workpiece, right? But at the point where we're forming the chip, it's moving straight through the workpiece, right? It's moving through the workpiece in that velocity direction. What's V? Equal to? So we got process variables, right? What's V equal to? V is equal to surface speed, whether it's a milling machine or a lathe. Now you say, what about the feed rate? Okay. There's a small part of V that's attributed to the feed rate. What kind of surface speeds are we talking about here? What's the surface speed for these AAD end mills that we're using for now? What does Kennemetal want us to move through the workpiece at? 6,000 feet per minute. No, we're not going that fast. But Kennemetal wants us to move them at 6,000 feet per minute. What's the feed rate? 6 inches a minute. 90 inches a minute. It's a lot less than 6,000, right? So there's a little bit of a component there, but we just ignore that when we do the modeling. This part of the class is about modeling. So that's our velocity. What's our power? So I got some force, right? Acting that direction. There's a force acting on the tool. There's also a force from the tool acting on the chip, from the workpiece. There's a force acting on the tool. We're going to call that FC. That's the cutting force. All right, so we're going to talk about, if we know the velocity, and we know the power, we can calculate the cutting force. That's kind of cool. Why might we want to know the cutting force? There. All right. Different materials may require different forces to cut them. Okay, because we started this with the question, if we wanted to estimate power, what might we need to consider in our estimating of the power? So if we want to estimate power, what do we need to know? We know that power equals force times velocity. We've got a material and we want to estimate the power. What do we have to know? What kind of factors are going to influence how much power it takes to make it happen? Go ahead. We might want to know how hard the material is. So we want to know some material properties, right? We want to know material properties. What else might we want to know? So what kind of properties about the tool do you think? So, tool, we're talking hardness, sharpness, ultimately that's going to be important, I suppose, how many cutting surfaces it has that are engaged in the workpiece at any point in time. Because what that's going to do is it's going to distribute the load among those surfaces. So if you've got 3 cutting surfaces in the part at the same time, that's going to distribute that. So that has some impact, sure. We need to know material properties, we need to know tool properties. So I said we're measuring the power that's going into the motor that spins the spindle. We need to know something about the transmission of the power from the input side of the motor to the cutting edge of the tool, right? So we need to know something about the tool design. We need to know material properties, tool hardness, tool, and so this is machine tool design. You guys smell this. This is a sharp. We need to know something about material properties, tool design, the tooling, the machine tool. Anything else you think you might need to know? What about the dimensions? So yes, but what about the dimensions? You get an idea? How deep you're cutting and how far in you're going. What I really want to know about is the material removal rate. So I want to know how much, so what that volume of material removed is going to tell me is, well, it's going to tell me how big the chips are. One way you can estimate the material removal is to measure how big the chips are. You can look at that. How do we know what the material removal rate is? Second. Yeah. Yeah, I don't know what the 12s and the 5s. We're gonna make all the units cancel. But what we got is, so if it's a milling machine, it's basically the cross-sectional area of our cut, right? So that's depth of cut times width of cut times the distance over time, because we want a volumetric material removal rate, right? So we've got to have time in there. And so the distance over time is the per minute feed rate, which if you're going from RPMs with inches per fluid, then you got to do that conversion to 12s and 5s. All right, so these are the kind of, so how do we know what all these things are? Because your job is to estimate the power it takes to make the cut. Your boss does not care what you need to know in order to estimate the power it takes to make the cut. Your boss wants to know, can the mini mill make the cut? And come on, because we're just about to set it up, and we got to ship parts this afternoon. Right? We're manufacturing engineers. We're about getting parts out the door. So how do we know the answers? How could you find out all these things? Look them up. Yeah, we could look them up in a reference manual. I mean, we could, last week we talked about science, right? We could write the reference manual. But I learned that early in my career as a graduate student, actually, that a few years in the lab could save you a few days in the library. And now with Google, it's sort of exponentially faster. Nobody laughs. Perfect joke. You guys know that if you want to name this class, you have to laugh at my jokes. And you have to shout out your name while you're laughing so I know who it was. All right. So what we're going to do, the resource that we're going to use to look this stuff up is the Machinery's Handbook. If you Google or YouTube search, did you know that YouTube is like the second largest search engine on the internet? Bing is not. Despite their attempts. I don't know if that statistic is still true, but about a year ago, somebody put that out there. They had data to back it up at that fact. You could either Google or YouTube search WPI Machinery's Handbook. And it will show you how you can have access to Machinery's Handbook for no cost, except for that $50,000 tuition. But it turns out our library pays millions of dollars a year, that's where a lot of that tuition goes, to have electronic access to a lot of reference books like this. And so the other way you can do this is you don't have to watch my YouTube videos to show you how to do it. You could, in fact, just go to the library webpage and go to their search thing and type Machinery's Handbook. It's okay if you spell it close, they figure out what you mean. And then you want to find the electronic version and you want to click on it and open it up. The stuff we're looking at is, and I think it's 28th edition, it's on the library webpage. The stuff we're looking at is around page 1054. Pretty sad that I remember page numbers in a book that's got like 3,000 pages. But somewhere right around page 1054, you're going to see this equation. And it's power of the cut. So it's the power going into forming the chip. And that equals this Kp value. Kp is a material quantity. So it's about the material. It's going to have information about, so Kp is what we call the specific power, and it's got units. It's going to have information about a feed factor. Somebody said it matters how fast we're moving through the workpiece. So besides the material removal rate, they have determined that if you're feeding faster, it takes a little bit less energy to make the cut. And if you're feeding slower, it takes a little bit more energy to make the cut. They figured that out experimentally. You want to know the volumetric material removal rate. And there's these tool wear factors. I love these kind of factors. We went through who did thermo, or not thermo, but thermo fluids classes, right? I love these tool wear factors, and they just sort of, yeah, the numbers don't work right unless we add this factor in. So those bunch factors in engineering and science. We have these factors here. Yeah. So with the information on or around page 1054, if I gave you a workpiece material, a type of tool, and a type of cutting operation, you should be able to tell me how much power it takes to make that cut now. Did we learn anything? I don't know. I taught something. I don't know if you guys learned anything. So please take a look at your grades and grading. I know some of the the most recent CAM exercise didn't get graded. So if that was the case, then that should be graded shortly. We remind the graders that that's due. The idea is that by Tuesday every week, we know everything about our grades from last week, so that if there is a problem, we take care of it in a timely manner and don't wait until the day after the term is over and all that. I mean, we could make our own YouTube video. There you go. We do have class tomorrow. We do have class tomorrow, 1 for 2 to 9. 1 for 2 to 9 class tomorrow. We will talk more about modeling manufacturing processes. We will talk about how the chip forms on the edge of the tool and the forces and powers and how we can understand those.